Hello everyone and welcome to this video. Today we're gonna cover the curl and divergence, and so in this section we are going to introduce a couple of new concepts which are the curl and the divergence of a vector. And so let's start with the curl. Given the vector field f equals pi plus qj plus rk, the curl is defined to be curl f, which is ry, which is the partial derivative of I with respect to y, and then qz, partial derivative of q with respect to z, times I plus pz, and so partial derivative of p with respect to z minus the partial derivative of r with respect to x, and now r here, qp, plus qx, which is the partial derivative of q with respect to x minus py, partial derivative of p with respect to y. This is basically defined as the curl of f. And so this is the curl of f, and we know that, or we can see that this is the gradient, called the gradient, and it's basically the partial derivative of the partial so the partial derivative in x, okay, in the I component, and the partial derivative of y in the j component, partial derivative of z in the k component. And so this is basically if we say gradient of f is basically partial derivative of f with respect to x, f to y, f to z. And so the curl f is a partial derivative, is the gradient times f. Yeah, so curl of f is just a gradient cross f, okay. And so this is ijk, and then partial derivative, as you can see, is basically the cross product. And so curl of f is just gonna be cross f, and then that's gonna be ijk, partial derivative of x, partial derivative of y, partial derivative of z, pqr, as you can see, and that's basically it. And then we have r y minus q dz, and that's basically in the I direction, and then we're gonna have it, that's basically what we have here, that's here, okay. And so yeah, so the curl of f is just the gradient crossed with f. And so if f of x, y, z has a continuous second order partial derivative, then the curl, which is that the gradient of f equals 0. Okay, so the curve of the gradient is 0. So if f has a continuous second order partial derivative, second order, okay, so it's not the first order, so it's fxx, okay. If it has that, then the curl is just 0, or the curl of the gradient is 0. And so this is easy enough to check by plugging into the definition. Okay, you can use the definition, and we can basically see that from here we can just prove that into the definition of the derivative. So we'll leave it to you to check. And so if f is a conservative vector field, then the curl of f equals 0. This is a direct result of what it means to be a conservative vector field and the previous fact, as you can see. So if f is conservative, then the curl of f is equal to 0. And this is the direct result of what it means to be a conservative vector field and the previous fact. And so if f is defined in all of R whose components have continuous first order partial derivatives, and the curl of f equals 0, then f is a conservative vector field, which is not easy to verify, and so we won't try it. And so these are the three rules. If f has a continuous second order partial derivative, then the curl of the gradient is 0. And if f is a conservative vector field, then the curl of f is 0 also, the curl of the function f itself, okay. And basically this upper f is just the function, so yeah, so it's just the function f, as you can see. And this is the direct result of what, yeah, conservative. And then 3, we have if f is defined on all of r to the 3, okay, so r to the 3 here, okay. If the components have continuous first order partial derivatives and the curl of f equals 0, then f is conservative field vector, which is not easy to verify, and we won't try. And so example 1, determine if f equals x squared yi plus xyz j minus x squared y squared k is a conservative field. Now to do that, we need to check if the curve is 0, or if the curl is 0. And so to check that, let's just do let's find the curl of this. So the curl of f equals basically the gradient crossed by f, and so we have ijk, and now ijk, as you can see. Okay, so the partial derivative with x, partial derivative with y, partial derivative with z. Okay, and so there is the p q r. That's the curl of f. Okay, and so we have the r, or let's just say ry minus qz I, and then minus rx, okay, minus pz j plus okay, so qx minus py, okay, and that's basically the k. And so now if we find out that this is 0, then the vector field is conservative, and so let's find this. And so ry, what is ry? Now this is pqr, and so ry with respect to y is just 2x squared y minus, okay, qx, which is 2x for xy, yeah, 2xy. Okay, and so we have rx, which is minus yeah, so minus 2xy squared, okay, and then I hope this gives us a conservative field, and so minus pz, which is, so this is 0, okay, and okay, so I don't think this is gonna give us 0. Yeah, so ry minus rz, as you can see, ry 2x squared y, okay, minus qz, okay, actually qz, yeah, qz is just, yeah, it's just xy. Is it PQR? I think it's, yeah. Yes, it's PQR. And so we have ry, as you can see, and it's gonna be in minus, so minus 2x squared y minus qz, which is xy, okay, I, minus, so rx is minus 2xy squared minus 0 plus qx is just yz minus py is gonna be basically x squared. Now this is not 0, it's not 0, so I would assume it's not conservative. And now okay, so this is not conservative, okay, perfect, love it. Now that's very easy. We can just check the curl, and if 0 we can say it's conservative, it's not conservative. Okay, actually, is there a different way to check? I think that's the way. Okay, now let's check. Okay, so here he wants us to show that this function is conservative, and he wants us to find a potential function f such that f equals the gradient of f. And so let's do curl of f, the gradient crossed by f, it's gonna be ijk, and then it's gonna be d over dx, and then d over dy, d over dz, and then pqr, PQR, and yeah, so for the I is just ry minus, okay, so let's do it directly. So first we have ry, and we have 9xy squared z cubed. Okay, minus qz is just 6xyz squared. Okay, and then we have qx, which is, as you can see, 0 minus pz. Okay, so we're gonna block this, so pz, which is 3y squared z squared. Okay, and then we get plus, for the k is just qx 2yz 3 minus, and we're gonna get py, so py is just 2yz to the 3 also. Okay, so just check one of the, okay, so here we get 0, so this is 0. And now for the j, let's just check the j. So r is just 3xy to cube. With respect to x, is just gonna be 3y cubed z cubed, 3 y cubed z cubed, minus, we're gonna then get pz. So pz is just 3. Yes, okay, so now this is correct. 3y squared z squared. Now, okay, so we get squared with respect to z. Okay, and for the y we have just ry, pqr ry 9x y cubed y squared z to the 3 minus, okay, so minus qz, now pqr, so q with respect to z is just 6 by 6y xyz to the cube. Okay, and okay, so we get here 0, we get here some other value, so let's just check. Okay, so I'll need to check this, come back to it. Okay, and I will tell you what we'll do. So let's now talk about the divergence of f, which is just basically a partial derivative of q with respect to x, partial derivative of q with respect to y, partial derivative of r with respect to z, and the divergence of f equals the gradient times f. And so example 2, compute the divergence of f for f equals x squared yi plus xyz j minus x squared y squared k, when the divergence of care f is just 0. So yeah, so if we compute the divergence of, so the divergence of a curl of the function is just gonna be 0. So example 3, verify the above fact for the vector field f equals yz squared plus xy plus yz. And so the divergence, okay, which is the gradient times the gradient of f is f of x, f yy, f zz. And then we have shown that the vector field f cannot be written as the curl of another vector field. So f cannot be written as the curl of G. Okay, so vector form of Green's theorem, as you can see. On domain, the following are equivalent. So f is conservative. As you can see, the integral is independent of path. As you can see for every piece. Okay, and so this is a theorem. And the vector form of Green's theorem, as you can see, this is the vector form of Green's theorem. Okay, and yeah, so f is conservative, the integral f dr is independent of path, f dot dr for every piece smooth close. Okay, yeah, and so this is our also surface integrals that we can find. Okay, line integrals, double integrals, triple integrals, we studied these. And we can find the surface integrals with just these. And so the surface integral function over surface is denoted as the following. This is the surface integral, and ds is just square root, is just the square root of gx squared plus gy squared plus 1. This is just ds. Now this is the evaluation theorem. Okay, and so as we said here, fx, fy, and we have the function g of x. Okay, and then so we have this, as you can see. Now this is the proof. Okay, so f equals 1, the surface integral equals the area surface, as you can see. So evaluate the surface integral where s is the surface. Now this is the surface, as you can see, and we want to evaluate, so we're gonna see here. So we're just gonna put y and then ds. Okay, we're gonna find zy, so it's 2y all squared plus 1 all squared plus 1, and that's basically how we evaluate. So of course dA, now this is gonna be dx dy, and we're gonna have the limits. The limits are these, so we're gonna have 0, 1 and 0 to 2. Now this is our surface integral. Okay, and that's basically our definition. Surface integrals, as you can see, so we want to evaluate some surface integral. So this is the surface and we want to evaluate it. And so let's see, here we have the evaluate. So cone z squared. Okay, now this is the cone and we want to evaluate x squared z ds. Now z, we can just plug in z that we have here, so we have z x squared plus y squared, and then just ds, we're gonna find a partial derivative, which is z equals square root of 2x squared plus y squared. Okay, and that's it. I think that's all. So we covered everything. This is the surface integral and the other integral. Okay, yeah, so that's it. Thank you for watching. See you in a different video.